Bismillahirrahmanirrahim. Assalamu alaikum. The second lecture of this course is Bayesian inversion. We finished the part of extension regime, okay, in 2 lectures, and now we are starting in what's called Bayesian inversion. Inversion means change of tectonic regime from extension to compression, or from compression to extension. Okay, so shift from one regime to another regime in the same area means inversion. So if we have area under extension and later on it's subjected to compression, it's called positive inversion. Okay, this term is very important. Region affected by extension and subsequently subjected to contractional deformation extension make fold, then compression make folding like this. It's called positive inversion. Okay, we have another type of inversion. It's called negative inversion. Negative inversion means area undergone compression and later on subject to extension mean negative inversion. We have two different inversions. So region which suffered from contraction in the first and later underwent extension is said to have experienced negative inversion. Inversion is very important in the petroleum industry because it provides good trap. Later, inshallah, you will know what the meaning of trap. Trap is the place in which hydrocarbons accumulated. So trap is usually be structural trap. And most common trap is folded trap, which deformed usually by Bayesian inversion. Okay. So, positive inversion or Bayesian inversion is very common in petroleum industry. Very important. Okay. If we have a look on this section, in extension regime, we divided the stratigraphic section or stratigraphic pattern in three package. Package proof before rifting and give it name pre-rift sequence, this one. Okay, and the section developed during extension, it's called syn-rift sediment, and section before rifting is called post-rift sedimentation. So the accommodation due to displacement on these faults resulted in a space who received sediments during a syn-rift. So that this package is syn-rift package. Okay. If we invert the movement on this fault from extension, downward movement to upward movement like this, we have two features, very important feature. First, the rift sequence here will be folded like this, syn-rift and post-rift. Okay. And the distance between displacement, vertical displacement between the pre-rift point before and after inversion decreased. Okay, and during inversion itself, because it's compression, we have another sequence package developed, what's called syn-inversion section, white one, and post-inversion section without any effect of tectonics, no post-inversion sedimentation. Okay. We have a very important point, what's called null point. Null point, it's a point on a marker without any effect of faulting. No displacement. A marker that appears unfaulted on the fault plane is a null point. Very important. You have to focus on the meaning of null point. Very important. Null point is point on a marker that indicate unfaulted, non-displacement, no offset. Normal faults, null points is always located in the upper most section of, okay, because normal faulting, this is normal fault. Why normal fault? Because displacement vertical down tip, okay. Hanging will move down, okay, to become down thrown block. Usually null point be at the tip of vertical tip, upper part of the fault tip is called null point in normal fault. If we invert these faults, okay, so the null point will move from upper to another level, this one. With continuous movement, null point will move down, and so on and so on and so on, okay? Here we have two segments of faults. Above the null point, the fault give reverse sense of movement. Below null point, the fault give negative or normal sense of movement, okay? So when normal fault is reactivated in reverse during reactivation due to reversing inversion of tectonic, null point moves downward. The final fault is reverse fault, combustion technology. However, above the null point, reverse fault has reverse geometry. Below the null point, reverse fault has normal geometry. In general, this fault now become reverse. But the appearance of faults above a null point is reversal geometry. Below null point is normal geometry. Okay? This diagram is very important to you to understand it. Here also we have the faults, okay, which was extension faults one time and now inverted, so become reverse fault now, contractional fault now. Null point is here, so this part above null point display reversal geometry. This part of fault below null point display normal geometry. Okay, and we have here syn-rift sequence, post-rift sequence, and so on. Okay, you have to understand it. All of this sequence we displayed. Example of this is seismic profile, type of geophysical tools which display subsurface in vertical section. Okay, so we have a fault here, major fault with inversion. Okay, it's another example, very nice. Okay, because this fault was extended. Why it's inversion? Because usually syn-rift sequence be thickest part of the sequence be unfolded like this. One of the criteria of inversion is what's called snake heads fold. Gross thickness of syn-rift sequence if compared by foot wall of the fault. Look at the syn-rift sequence here. The folded sequence is very big than or greater than the thickness of syn-rift sequence in the foot wall of the fault. Okay.